In this video, I want to talk about Hindu Arabic numerals, as well as some information about place value and vocabulary. First, a little math history. The Hindu Arabic numerals were invented by the ancient Indians. By Indians here, I mean the people who live in South Asia. I don't mean Native Americans. Hind was the European name for India at that time. That's the same root that the word Hindu or the word Hinduism, referring to the religion or actually group of religions that emerged in India in ancient times, comes from. Those Hindu numbers were brought to Europe by Arab traders in the Middle Ages, what we call the Middle Ages. By the way, Arabic is the language, Arab is the ethnicity. Before then in Europe, Roman numerals had still been used. This was centuries after the Roman Empire ended, but Roman numerals were still used in Europe. And Roman numerals are hard to work with. They are hard to do arithmetic with, particularly things like multiplication. It's possible to do multiplication with Roman numerals. I've seen descriptions of it. I think I've even seen videos where people have done it. It's not something that a person would choose to do. It is much, much harder. Sometimes, especially in older works, Hindu Arabic numerals are just called Arabic numerals. In most modern works, we refer to them as Hindu Arabic numerals, representing both their origin as well as the people who brought them to Europe. And Hindu Arabic numerals today are the numerals that are used throughout the world for the most part. I do want to point out, though, that if you have students who have attended school in different countries, although those countries almost certainly use Hindu Arabic numerals, they often write them differently than they are written in the Western world, than written in European countries and countries that speak European languages, including the United States. So you might have students from India or from Japan or from Indonesia who might use Hindu Arabic numerals, but who write them differently than you would expect them to be written. So they need to be taught how to write them in the way that they're written in the United States, but you need to recognize that sort of along the way. Obviously, there are also numerals in other alphabets as well, and so I say the Hindu Arabic numerals are by far the dominant. That is not to say there aren't still others being used in places around the world. So, what makes the Hindu Arabic numerals unique? Why have they been so successful? Obviously, part of it is due to European colonialism, but beyond that, what made them successful in ancient India, in Southwest Asia and North African regions that were controlled by Arabs or that Arab traders visited, and then eventually to Europe. So, what makes Hindu Arabic numerals unique? What are some of the reasons that have caused them to be the dominant numeration system in the world today? Obviously, part of the reason is due to European colonialism and imperialism, but the system did not originate with Europeans. So, actually, there are several things that make this system unique that are reasons why it's still in use and why it will likely continue to be in use. I want to talk about some of them. One is that it has a place value system. Place value systems are relatively rare in historical numeration systems. A few cultures' systems had place value systems. The Mayan numeration system used place value. Your textbook talks about different bases. The Mayan numeration system used base 20, more or less. The Babylonian system had a place value system, and the Babylonian system used base 60, more or less. And in fact, the Babylonian system is why today we still have 60 seconds in a minute and 60 minutes in an hour. Those are holdovers that have lasted through the millennia from the Babylonian system. In a place value system, a digit's or symbol's location determines its value. So, for example, if we skip down to the bottom of this slide, For example, in the number 123,456 and 789 thousandths, the digit 3 is in the thousands place. So it has a value of 3 times 1,000, 3,000. If that digit 3 were moved one place to the right, it would be in the hundreds place, and it would have a value of 300. If it were moved one digit to the left, it would be in the 10,000s place, and it would have a value of 30,000. And then the digit 8 is in the hundredths place, so it has a value of 8 times 100th, or 8 times 1 over 100, which is 8 hundredths. So this is the idea of place value. Where a digit is in a number determines the value of that digit. The other thing that makes the Hindu-Arabic system unique, and that the Babylonians did not have, although the Mayans did, is the idea of zero. Zero as a number. Zero not simply as the absence of something, but zero as an actual number. The idea of zero was invented independently by both the ancient Indians as well as by the Mayans. And as far as we know, those are the only cultures that invented zero. There are some math historians who argue that the ancient Persians also invented zero, but it appears, and I'm not an expert in this area of math history, but it appears that zero there had really limited uses. It wasn't widely used in any sort of number system or numeration system. So I mentioned that ancient Mayan numeral systems are based on base 20, and the Babylonian system was based on base 60. The Hindu-Arabic system is based on base 10. And each place value is, in fact, a power of 10. And excuse me, and they go on forever in both directions. That's what the ellipses mean here. So these 3 dots, which in English means we've left something out, in math means this pattern keeps going. So for example, this is 10 to the 3rd power. To the left of it would be 10 to the 4th power, then 10 to the 5th power, then 10 to the 6th power, then 10 to the 7th power, and so on for infinity. And then here we have 10 to the negative 2nd power. To the right of that would be to the negative 3rd power. To the right of that would be 10 to the negative 4th power, then 10 to the negative 5th power, and so on for infinity. Other bases use other powers. Base 5, for example, uses powers of 5. So a number written in base 5 would be 5 to the 3rd plus some number times 5 to the 3rd plus some number times 5 squared plus some number times 5 to the 1st, and so on. Here's another example. This is the number 983 and 105 thousandths. And so in terms of place value, this is 9 times, this is essentially expanded form, 9 times 10 squared, or 9 times 100, plus 8 times 10 to the 1st, or 8 times 10, plus 3 times 10 to the 0, or 3 times 1. Remember, any number to the 0 power other than 0 is 1. So 10 to the 0 is 1. 20 to the 0 is 1. 5 million to the 0 is 1. Any number to the 0 power other than 0 is the number 1. So 3 times 10 to the 0, or 3 times 1, plus 1 times 10 to the negative 1st, or 1 times 1/10, plus 0 times 10 to the negative 2, or 0 times 1 over 100, plus 5 times 10 to the negative 3, or 5 times 1,000. Usually in elementary school, when we teach expanded form, we're only dealing with whole numbers. We aren't working with decimals until middle school at the earliest. Typically for expanded form, we teach decimals in like 5th grade, 4th and 5th grade, but we don't necessarily go into expanded form with them until a little bit later. But it depends on your curriculum. There's disagreement about what to do with zeros in a number like this. I always, when doing expanded form when I teach, will always include it, because otherwise my students will skip it. And so they would write this as 0.15 if I didn't have 0 times 10 to the negative 2 here. So I will include zeros in expanded form. Sometimes this is condensed more to something like this: 900 plus 80 plus 3 plus 1/10 plus 0 hundredths, and this should be plus 5 1,000ths. Let me fix that. There, sorry about that error. A little typo there. In elementary school, we usually only write whole numbers in expanded form. We typically don't worry too much about the decimal part. I also do want to point out a little math methods thing here when we're talking about numbers, like this number or any number. The word "and" only refers to the decimal point. And in sort of informal speech, we often put "and" elsewhere. We say something like 456 or 123,456. We put "and" in different places. But in math, "and" refers to the decimal point. So again, this number is 123,456 and 789 thousandths. So one more time, 123,456 and 789 thousandths. So many world systems did not use place value. The Roman numeral system doesn't use place value. Now, it's still built around the idea of tens, but it's also built around the idea of fives. So the Roman numeral system has digits for 1, 5, 10, 50, 100, 500, 1,000, each of which are represented by a letter. Similarly, the Egyptian numeral system used hieroglyphs to represent different values, but they were powers of 10, but they didn't use place value. They just wrote as many of those as they needed. So if whatever the symbol was for 100, if they wanted to write 500, they would write 5 of those symbols. Your book might talk more about the Egyptian numeration system. I honestly don't remember if it does or not. So some other numeral systems around the world are built around base 10. Math historians tend to believe that's because we have 10 digits on our hands. But they didn't necessarily use place value. So something that makes the Hindu-Arabic system somewhat unique. That it both uses base 10, and it has place value. It both uses base 10 and it has place value. So any number in a base 10 system can be created by using 10 digits. And those digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. With those 10 digits, we can create any number. Obviously, for numbers less than 1, we have to also use a decimal point. For negative numbers, we have to use a minus sign and things like that. But essentially, for any counting number, for any number that we can count as big as we can possibly imagine, we can create that number by using some combination of 10 digits. This rule is true no matter what the base is. So for example, base 2, which is used by computers, uses just 2 digits, 0 and 1. Base 5 uses 5 digits, 0, 1, 2, 3, and 4. Notice that 0 is always a digit. And notice that the base, the number after the base tells us how many digits it is. And the biggest digit will always be 1 less than the base. So in base 5, the biggest digit is 4. In base 6, the biggest digit would be 5. If we used base 100, which we don't, thankfully, that would be a nightmare. But if we did, the biggest digit would be 99. So in base 10, 10 digits, which are 0 through 9. 10 itself is not a digit. 10 is composed of 2 digits, the digit 1 and the digit 0. Using digits is something that makes Hindu-Arabic numerals unique compared to most other number systems. There are some more special bases that are sometimes taught, not so much in elementary school anymore, although that may vary depending on how important coding is in a school. But base 8, which is sometimes used by computers, for example, the digits there would be 0 through 7. Now, what do we do for bases bigger than base 10? Because we've run out of digits. In that case, we use letters as digits instead of numerals as digits. So, for example, in base 11, we use the letter T to represent the number 10. In base 12, we use the letter T to represent the number 10, and we use the letter E to represent the number 11. Let me fix my typo here. This is something that is actually mentioned in your textbook. There's not actually a hard and fast rule for what letters to use, but your textbook uses T for 10 and E for 11, and that is mentioned when it talks about different bases. Different textbooks might use different letters, and so that would be specified somewhere in the textbook. Now, the most common base is base 10. Binary or base 2 is common as well because computers use it, but it's hard for humans to use because the binary numerals get really long really quickly. And conversely, the bigger the base, the shorter the numerals are going to be, the shorter the representations of numbers are going to be. And so many computer systems will use base 16. And in base 16, we use the letters A through F for numbers more than 10, or for 10 and more. So A represents 10, B represents 11, C represents 12, D represents 13, E represents 14, and F represents 15. If you've ever worked with computer graphics, for example, very often colors on a computer are represented in hexadecimal to get really specific to things. And so sometimes in graphic design, they actually talk about this a little bit. Some books will use this system for others as well, and they ignore T and E. I kind of like that approach. It's a little simpler. So A is always 10, B is always 11. But I believe your book uses specifically T to represent 10 and E to represent 11. Again, it talks about it in the chapter on bases, what they use. I want to end with some vocabulary. Please be very clear about vocabulary related to place value. So hundreds, tens, and ones refer to whole numbers. Sometimes ones are referred to as units. You should use, when you teach, whichever term your curriculum uses. So if your curriculum uses ones, you should refer to the ones place. If your curriculum uses units, you should refer to the units place. So these are whole numbers. In other words, numbers 0 and above. These are numbers to the left of the decimal point. And obviously these are in lower elementary school numbers that don't have a decimal point because we don't include a decimal if there's nothing to the right of the decimal point. Now, words like tenths, hundredths, and thousandths refer to decimals less than 1, numbers to the right of the decimal point. This is something that students often get wrong in this class when they talk about this. And when they're talking about place value, they talk about tenths, but they are talking actually about tens. So please make sure you distinguish these. Make sure you spell them correctly. This spelling matters. There is no such thing as oneths or uniths. Students often think there is. And that makes sense. Like we expect that to be the pattern. Right, we go to the left, ones, tens, hundreds, thousands. But then to the right of the decimal point, we don't start with ones, we start with tenths. So to the right, we go tenths, hundredths, thousandths, 10,000ths, 100,000ths, millionths, and so on. And you see even here with the captioning doesn't always get this right. So 100,000ths. There we go. You have to really enunciate this and again, use it spelled out as you're talking about it. And the final vocabulary thing to talk about is the difference between numbers and numerals. They are not the same. We often use them as synonyms for each other, but we shouldn't. And I am guilty of this as well. I try not to. Numbers are abstract concepts. These are things that cannot be experienced directly through the senses. In other words, we can't touch or taste or feel or smell a number. We can't look outside and see, look, there's a flock of threes flying through the air. Oh, look, I see a 2 on the ground. Numbers are abstract. So to represent numbers, we use numerals. Numerals are number labels. I remember this because the word numeral ends in L, just as the word label starts and ends with L. So numerals are number labels. The digits that we use to create representations of numbers are numerals. So for example, 4 tally marks is a numeral representing the abstract number 4. The Hindu Arabic digit or symbol 4 is a numeral representing the abstract number 4. The Roman numeral IV is again a numeral. It is a label. It is a group of letters that represents the number 4. Now, I sometimes think of words for numbers as also numerals. That's not technically correct, but they aren't numbers. And what we usually call them are number names. So, for example, 4 is a number name in English for the abstract number 4. Different languages have different number names, right? Different words in that language. So in Swedish, for example, the number name for 4 is fyra. In Spanish, it is cuatro. And if you speak fluent Swedish or Spanish, I apologize for my pronunciation of both of those words. So number names aren't really the same as numbers either. Those are also labels, essentially. They aren't the number themselves. The number is the abstract concept. So if someone asks you the difference between numbers and numerals, a number is an abstract concept. You can't actually encounter it with the senses. You can think about it. It's sort of like abstract. It's sort of like emotions, right? Things like love or fear, anger, sadness, happiness, joy. These are things that are abstract. We can talk about them. We can provide examples of them, but we can't actually see it. We can see examples of it, but we can't see the actual thing. It's abstract. Same thing for numbers. So when we label numbers, the digits that we use are numerals. And finally, a fun fact. I mentioned that Hindu Arabic numerals are traditionally called Arabic numerals, especially in older works. And there are occasionally surveys done. And surveys, for example, have asked people in the US if they support stopping or decreasing the instruction of Arabic numerals. And people overwhelmingly say, yes, we should stop teaching Arabic numerals. That's terrible that we teach them. They believe that they are quote unquote foreign. They are not. They are the numerals that have been used for centuries, for over half a millennium. I think they were introduced to Europe. I want to say I recently read it by Fibonacci, but at least around that time. So around the 1300s probably is when they first get introduced to Europe. They were unpopular at first. People don't like change. But they've been around for a very long time. And so when people say this, this really represents a state of math illiteracy as well as a state of ethnocentrism in the country. I hope you found this useful. If you have questions about Hindu Arabic numerals, please let me know. Thanks for watching.